Hello, welcome back. In this video, we are going to talk about the entropy associated with expansion processes. Okay, so in the last set of videos, we talked about the second law of thermodynamics. And in this, we said that spontaneous processes are the ones in which the total entropy increases. And so we could write this as S total. And so if we started here and we did nothing to the system, we just watched it, the system would move towards equilibrium. And equilibrium is when the entropy is maximized. Okay, so in an isothermal expansion, we're going to think about how an ideal gas undergoes an isothermal, so constant temperature, expansion from an initial volume to a final volume. And in this, the final volume is greater than the initial volume. During the expansion, the energy of the system does not change. Okay, so this means that the total energy of that system is constant and this happens because there's no interaction between the molecules. And so we can say that dE is equal to TdS minus PdV, and that is equal to 0. And so since that is equal to 0, we can rearrange this, solving for ds, and get that ds is equal to P over T dV. Then this is the ideal gas law. Rearranged. And so all I did was I plugged this in here and apparently I don't know my ideal gas law. This should be volume. So when I plugged that in, I get that ds is equal to nr over v dv. And this is convenient because that means that I can integrate. And so if I integrate both sides of this expression, I get that delta S is equal to nR times the natural log of VF over VI. So if we are doing expansion where VF is bigger than VI, so our final volume is larger than our initial volume, then the natural log of VF over VI is bigger than 0. And this means that the entropy is greater than 0. And that is our definition of a spontaneous process. And so no work is needed in order to increase the volume of the system. Now, likewise, in compression, if we have this reverse so that our volume becomes smaller, then this natural log is less than 0, delta S is less than 0, and this is a non-spontaneous process by definition of the second law of thermodynamics. And this means that in order to reduce the volume, work has to be done. So entropy is not going to drive that process. Instead, some sort of external work is going to have to go in order for the compression to occur. Okay, so I'm going to walk you through an example. The example is to find the entropy change when 2 moles of helium is expanded from 2 bar to 1 bar at 298 Kelvin. And I give you values for the ideal gas constant. Okay, so the first spot to start is to convert our pressures to volume. And so step 1 is convert P to V. And we're going to do this using the ideal gas law. So when we do that, we get that our initial volume is 24.8 liters, and our final volume is 49.6 liters. And so now we have the information that we need to plug things in to our delta S of expansion equation. And so we plug and chug, and we get that delta S is equal to 11.5 joules per Kelvin. And since delta S is a positive number, we know that this process is spontaneous, which is what we would expect because we are working with an expansion.